All right, hello everyone. We've reached the top of the hour, so I think we can go ahead and get started. Thank you everyone for joining us. This is part of our Veris Engineering's webinar series. We'll be talking today about this is kind of a I call Introduction to Polymer Material Structure and Characterization. So thank you all for joining, and let's dive right into it. Just a few notes before we get started. If you have a question as we go through the webinar, the best way to do that is to use the Q&A feature in Microsoft Teams. So you should, if you can click on that, should be somewhere near the top of your screen, and put your question in there, and then I will kind of get to those as I wrap up the sections, or any I missed, I'll go to the end. And just because sometimes I do kind of miss things during the presentation, please just put the slide number in your question, so you can say something like on slide 15, question about whatever I was talking about on slide 15, and that'll help us kind of go back and make things a little bit more efficient. And just one final note is that the class is going to be recorded today, so hopefully soon, either kind of later today or tomorrow, you should also receive a link to the recording, assuming we have no problems with the recording, which has happened, but I think we should be okay. So just to kind of go over a brief agenda for today, the actual kind of webinar targeting about 45 minutes. My line got off a little bit there on that, but start with just a very brief introduction to Veris Engineering. So we're a consulting firm. I'd like to talk just a little bit about the kind of services that we offer, which kind of dovetails into kind of why we're presenting this webinar today. And we kind of have the actual webinar itself. The core of it is kind of split into two parts. So we have the first part, we're going to talk about the structure of polymer materials, sort of things that kind of based on my experience working with clients, I feel like mechanical engineers need to know. And then in the second half, we're going to talk a little bit more about characterization methods. That directly follows the first half, where we're going to talk about, aspects of polymer material structure, and then we're talking about how to measure or characterize those aspects of the structure. And we'll leave about 15 minutes at the end for a Q&A, although we may end up, letting that bleed into the main talk if people ask questions kind of as we're going along. So feel free to drop those in the Q&A tab. So just a brief overview of Veris Engineering. So we are an engineering consulting firm based just outside of Boston here in Massachusetts. And we have kind of a large array of multidisciplinary subject matter expertise. So everything from engineering, simulation, fluid dynamics, heat transfer and mass transfer, mechanics and structural mechanics and finite element analysis, simulation, things like that, going into our kind of laboratory activities, which is kind of more relevant to today. We have some mechanical characterization, materials engineering, as well as product testing and failure analysis. We're actually working with physical products in our lab, trying to help our clients understand essentially why they're not working and how we can help them bring that product to market. So we like to say about ourselves that we have kind of academic expertise, but applied on an industrial timescale. And just an introduction to me. Why am I giving this course? So I got my PhD in material science and engineering from MIT, kind of a background in polymer science and sort of core material science. My work is kind of highlighted over on the right in terms of our core offerings here at Veris, but I work in our test lab, work on kind of all of our materials engineering projects, as well as some of our failure analyses and product testing and things like that. And so I work with clients, on, kind of analyzing their polymer materials, helping them understand, why this material might be the correct one, why it might not be, how we can evaluate whether or not it's the correct one, why their device might be failing, and how their kind of products capabilities are informed by the kind of intrinsic material properties of the materials that they're using. So to kind of move right along. Just to go over our kind of overall learning objectives, there's a couple of bullet points just from a very high level. What I like to think about this course is that the materials chemistry and structure of polymers, plastics, and adhesives significantly affects their properties, and that's mechanical or otherwise. And so our goal during this session is to really survey polymer structure and characterization techniques from a very high level. Everything that we're going to talk about today, we have 45 minutes to an hour kind of set aside to learn these topics. And so any one of these topics is something that you could spend, a master's or a PhD or even an entire career working on. And so we're really trying to cram kind of everything I think a mechanical engineer needs to know about polymer science into an hour. So, certainly it is much more of a survey than a deep dive, but I'm hoping that by the end of the class, you'll be able to at least, be able to classify and describe polymer materials kind of by their structure and have some, understanding of how we can use analytical techniques to kind of measure those aspects of polymer structure, and kind of even, beyond that, understand how the aspects, those kind of different aspects of polymer structure inform the design decisions that you need to make as you're going through your product design life cycle and process. So to go into a kind of a more detailed outline of the specific topics that we're going to be talking about today, first half of the class on polymer structure, we're going to be talking first about thermosets and thermoplastics. We're going to talk about semi-crystalline polymers. I'm going to spend a little bit of time talking about kind of the glass transition temperature, or the glass transitions in polymers, because I think that's one of the things that is perhaps most often overlooked or not well understood, but has a really significant impact on functional performance of polymer materials. And so with that kind of structure in mind, then we're going to move on to the characterization methods section of our webinar today. We're first going to talk about dynamic mechanical analysis, or DMA. Then we're going to talk about differential scanning calorimetry, or DSC, thermogravimetric analysis, or TGA, and Fourier transform infrared spectroscopy. And I will sometimes kind of tongue-in-cheek refer to these as the four horsemen of polymer characterization. These are kind of the four methods where, kind of anytime you have a new material or you're running into a problem, probably 2 or 3 or maybe all 4 of these are going to help you really kind of dig into understanding your material and perhaps at the very least starting your failure analysis journey. So, but first we're going to talk a little bit about polymer structure, and I want to talk a little bit about the word itself, polymer, right? We split that into 2 halves. We have poly, which means many, and mer, which means part, right? And so this is the idea behind polymers, that they're these really long chain molecules made up of many repeating subunits that are made from monomers. And so this is something that perhaps an experiment that you've done, it's used very often as kind of a demonstration in kind of introductory chemistry or introductory polymer courses, is the polymerization of nylon. We kind of mix these 2 monomers. You have your acid and your amine over here, and those are going to undergo a chemical reaction and a bond together. And so you can and you notice that there's a functional groups on both sides of each one of these molecules, and we're going to make these really, really long chains where you have this repeat unit that is kind of the core element of the nylon, but we make these really, 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 really long chain molecules. And both of the original components are liquids, but when we get this polymerization reaction, that's when we start to get that kind of more solid polymer. Obviously, as you go to much higher molecular weights, you're going to get those hard, strong engineering polymers that we like to use to make devices out of. You think about the molecular weight of kind of most engineering polymers, it's somewhere around this is 10,000 to 1,000,000 grams per mole. So much, much larger than other molecules you might have learned about in something like an introductory chemistry class. But that's kind of a rough molecular weight, let's say, average of many polymers that are out there. So now I want to talk a little bit about thermosets and thermoplastics. And so if you have ever had to manufacture something out of a polymer, this is something that you really, really need to understand. So the idea that all polymers are composed of these long chain molecules, but they differ in how those molecules are connected. So more specifically, in thermoplastics, the polymer chains are not chemically bonded to one another. So you think of your thermoplastics like a plate of spaghetti. You have these really long strands, they're all entangled with one another, and that's how they're actually kind of resisting deformation. It's those entanglements between chains that really help give the material itself its sort of stiffness and strength and all sorts of nice mechanical properties that we like when we make these kinds of devices. So there's some examples of thermoplastics, polyethylene, ABS, polycarbonate, or nylon. And the key thing about thermoplastics is that upon heating, the thermoplastics will kind of fully melt, or at the very least soften, and can be reshaped. So that's why when you do kind of a standard injection molding production process, you're almost always using a thermoplastic resin, because you can heat it up feed it through your extruder, goes into a die, then it cools, and now it's the nice shape of the part that you wanted. Other methods like extrusion, for example, similar sort of underlying physical process as injection molding, but it relies on the fact that these long polymer chains, when we heat them up, they can move more freely. We have kind of a more liquid-like material that can flow through a die, and then once it's cooled, those chains kind of lock into place because they're all entangled with each other, but they're not chemically bonded to one another. So we can keep reheating them and reshaping them and cooling them again up to a certain point. Now, in contrast, thermoset polymers are chemically bonded to one another. So we take our kind of long polymer chains, our plate of spaghetti, and we actually chemically bond all our polymers to one another. It's called cross-linking them. And so when we heat up this material, those bonds don't break very easily. And so the material can't really melt, be reshaped and reprocessed in the same way that a thermoplastic can. So things like epoxies or MMA adhesives, most rubbers tend to be thermoset materials because those polymer chains are cross-linked. And so that really reflects in what kind of processing methods can we use to make products out of thermosets versus thermoplastics, but also has some implications for some of their, for example, mechanical properties as well. So kind of moving from thermoplastics and thermosets onto semi-crystalline polymers, this is kind of the other aspect of polymer structure that I think is worth mentioning. So we have this kind of, I like to keep referring back to this spaghetti picture, this understanding of polymer material structure, is that the polymer chains, at different locations within a polymer can be in different states of order. So they can be oriented randomly, much like your plate of spaghetti, or they can be locally aligned with each other. And you see that in this cartoon image over here, where we have these kind of images where the polymer chains, or there's parts of the material where the polymer chains are kind of randomly oriented, and then these blue regions that are just there to kind of highlight that the polymer chains are kind of all going parallel in this region. And so those ordered domains, those are called the crystalline domains of the polymer. And so the kind of the key thing that I want to point out here is that all polymers contain amorphous domains. Some polymers contain crystalline domains, and so that's why we call them semi-crystalline polymers. There are, I would say, essentially no polymers that are 100% crystalline. Perhaps there's an edge case out there. Maybe I'll learn about it sometime soon. But for kind of practical engineering polymers, they're always semi-crystalline. That crystallinity can be as low as 10%, can go up to 60, maybe even 70% or something like that, just to give kind of a range there. But that's the kind of the key distinction between crystalline polymers and other crystalline materials like metals, where in a metal, for example, a steel or something like that, it's nearly 100% crystalline. Whereas in the polymer, it is never really kind of functionally going to approach that 100% crystallinity. And so you can imagine that these crystalline domains, semi-crystalline polymers, those crystalline domains, those molecules are more tightly bound together. So that tends to do things like increase the strength and increase the stiffness of the polymer. Just for example, because when those polymers are more tightly tied together, then it's more difficult for them to move. And kind of lastly, the actual degree of crystallinity of a polymer can vary pretty widely within a family. It depends on a lot of things. It depends on the actual kind of polymer chemical structure. It depends on additives that are blended in with the polymer, and even kind of the strain history. So if you take certain polymers and you actually stretch them, you have what's called, or they will actually nucleate crystalline domains because those polymer chains start to align if you stretch the polymer. So you can cause an increase in crystallinity in your material just by deforming it. So just to give a more concrete example about crystalline polymers and what that kind of means, maybe in a more tactile way, probably many of you are familiar with PET. It's kind of a naturally semi-crystalline thermoplastic polymer. And you can get PET sheets that are clear, which means it's been processed to prevent crystallization, right? So we're essentially, you take a sheet of PET and you cool it down really fast. You're not allowing those crystalline domains to form, and so that makes it clear. And generally, for a lot of things, especially in sort of thermoformed packaging, for example, you can see this picture on the right, you want that clarity, right? So you want, for this particular medical device, it's a pre-filled syringe, being able to look inside and see the product inside is a real benefit, or even in the case of sort of like consumer product packaging, you want someone to be going through the store and see your product inside the package. And so the clarity is really important. But semicrystalline PET, which is, you can see this this piece down below here, is opaque. So once we actually have a piece where the crystals have formed, it starts to turn white. And so generally speaking, if you have PET and you're using it to make thermoformed packaging, you need to process it in such a way that you avoid crystals from forming, because otherwise you're going to kind of ruin the clarity of your package. Okay. Now I'd like to talk about the glass transition. This is a kind of a thermal transition in polymer materials that is not really seen kind of what we call other engineering materials like ceramics and metals. So in semicrystalline polymers, the crystalline domains melt at a melting temperature, just like crystalline solids do. And so that you don't really need to think about that, in much more detail than that. But the amorphous domains, where there's not strong local ordering of the polymer chains, the amorphous domains are glassy. They're hard and strong. But then at high temperatures, the amorphous domains become rubbery. They're flexible and soft. And the glass transition temperature kind of defines that boundary between glassy and rubbery states with respect to temperature. And you can see that in this figure over on the right, where I'm showing you the modulus of the material as a function of the temperature. And so this in particular is an epoxy, a thermoset epoxy. And so this is a structural adhesive. This is something that you want to be, where you use it, you want it to be hard and strong. You want it to be glassy. But as we heat this up and go through TG, the glass transition temperature, which for this material is around 80 degrees Celsius, you see that it becomes flexible and soft. We've entered that rubbery domain. And you notice that the y-axis here is on a log scale, meaning that as you go through TG, the modulus is dropping from, in this case, it's about it's 1,000 megapascals, so that's about 2 gigapascals, down to about 20 megapascals. So 2 orders of magnitude drop over this temperature range. The other thing that I want to kind of point out is that if you're looking at the spec sheet for a material, it might list a glass transition temperature. Often they don't, but sometimes they do. And you might see for this material, the TG is listed at right around that 80 degrees Celsius. But where does this material actually start to lose its stiffness? It's at a much lower temperature, something closer to about 60 degrees Celsius. So in my experience, it's important to be really careful around the glass transition temperature of your material, because it can the sort of like functional softening the material can happen at a different temperature than the nominal glass transition temperature. And also there's almost like this window, from, let's call it -60 up to probably about 100 degrees Celsius, where you have this extreme temperature sensitivity of the modulus. So that means that a small change in the temperature of your material will result in a large change in the modulus. And so you can have wildly fluctuating material properties in your TG. It makes it really hard to make robust predictions about how your device is going to perform. So what I almost always, counsel my clients to do is avoid TG by at least 20 degrees. Basically, you either want to be well below it if you want a glassy, hard and strong material like this adhesive, or you want to be well above it if, for example, you have a gasket of some kind that you want to be rubbery. You want to have that kind of flexible and soft characteristic. So you want to be well above that TG, because otherwise you're going to start to get orders of magnitude increases in the stiffness. Your sealing performance is going to be worse, or your hand feel is going to be worse if that's something that you're concerned about. It's really, really, really important to avoid TG as much as you can. And to do that, you actually need to know what TG is first, which as I said, not every material supplier is going to tell you what TG is on their data sheet. It's usually something you have to figure out for yourself, in my experience. So kind of go over that, these two different kind of effective softening temperatures of polymer materials. This is just a cartoon laid out of how a semi-crystalline polymer will change its stiffness as a function of temperature. And so when we start at very low temperatures, we have glaciamorphous regions and we have crystalline domains as well. So we have a really high modulus. These are your polymers, your really strong engineering polymers that are, have essentially gigapascals of modulus. When we go through the glass transition temperature, we're going to get usually a couple orders of magnitude drop in the modulus. But depending on how crystalline our material is, we still could have a fairly high modulus. So this is the domain where things like polyethylene and polypropylene live, where the glass transition temperature is usually well below room temperature. But we have these crystalline domains that are still kind of operating to give our material the kind of stiffness and strength that we might want. But then once we go through the melting temperature and those crystalline domains melt, now we have something that is either very rubbery or very soft, potentially even kind of a viscous liquid. So this is where we're going to end up processing our material, assuming this is a thermoplastic. All right, so that's the end of the kind of first half of our presentation today on kind of material structure. So we're going to switch gears a little bit and talk about characterization methods. Keeping in mind everything that we just talked about with all the material structure. So the first technique I want to talk about is dynamic mechanical analysis, or DMA. I like talking about this one first because I find it to be it's the most intuitive, right? Because what this is functionally a mechanical test. So if we look at a sample setup here, this is set up in tension, where there is a specimen that's right here in black. It is kind of attached to kind of the upper clamp up here and a movable lower clamp down here. And what this movable clamp does is going to basically apply either a stress or strain to our material kind of as we want. And so everything underneath the hood here on our DMA, there's a drive system, sort of a motor, if you will, a position encoder that's usually in a DMA is kind of very fine, typically sort of like micron resolution or less, and a load cell that's going to measure the force. And so the contrast between the DMA and a sort of more conventional mechanical characterization is that the maximum load in DMA is usually small. And in our DMA, and this is a picture of our DMA in our lab, it is only about 18 newtons is maximum force. But what is where you're getting as a trade-off for that kind of low load resolution is very precise temperature control. So this kind of hood that you can see in the kind of upper part of this picture, and then over here in this left-hand picture, this comes down and creates basically a really tight furnace. And there are other sort of heating elements and gas flow elements in this upper hood that precisely control the temperature of the specimen. And so one of the things the DMA is most useful for is getting the temperature dependence of the mechanical properties of the material, of a soft material or polymer. And so this is showing the test in tension. There are other geometries. You can use compression. You can use a cantilever bending method or 3-point bend. You can design or purchase other fixtures for this, for the DMA, that do things like control the humidity or immerse your sample in a fluid or something like that. It's a bit beyond the scope of what we're talking about here today. We have lots of options for kind of testing the mechanical properties of material over that range of parameters. And in the DMA, there's kind of three basic tests that you might run. So one is an oscillatory deformation. So that means that this movable clamp is going to be applying typically a sinusoidal strain to the material, typically something with low amplitude, let's say 0.1% or something like that. And so what you're measuring is the dynamic modulus, the storage modulus E prime, and the loss modulus E double prime as a function of the oscillation frequency. If you apply a step strain, meaning that at time 0 you apply a fixed strain, let's say 1% to the sample, and then you measure the stiffness as a function of time, that gives you the relaxation modulus. If you apply a step stress, now we're in a creep mode. So at time 0 we apply a fixed stress, and then we're going to measure the strain as a function of time to get the creep. And so there's a lot more information on here. We're going to keep talking about the DMA a little bit, but this could be an entire webinar or even more than that about all the different things the DMA can be used for and all the different options that we have for it. But just to give a kind of a concrete example of what the data looks like on a real polymer and how we can use the DMA to identify aspects of material structure. This is some example data. This is on a nylon 6. And what we've done is measure the storage modulus and the loss modulus as a function of temperature over this wide temperature range. So we look all the way down to minus 100 C up to a little bit over 200 degrees C. And so the storage modulus, which is the solid line here, that's kind of roughly equivalent to the Young's modulus. The material sort of is technically not equivalent, but it's close enough for our purposes here. And then the loss modulus, which is essentially a measure of the kind of viscous energy dissipation that the material undergoes during one oscillation cycle. So essentially, that's why it's called the storage modulus. We have elastic energy. In the loss modulus, we have lost viscous energy. And as we increase the temperature, there's kind of two things that I want to call out here. There's point number 1 and point number 2. So point number 1, we see that the storage modulus starts to decrease kind of precipitously right at about 50 degrees C. And then we also kind of right there have a kind of local maximum in the loss modulus. And then at point number 2, the storage modulus and the loss modulus both start to decrease sharply. So what does this tell us about our material? So at point number 1, where we see this large decrease in the storage modulus, that is the glass transition temperature of the material, right? So this is kind of classic glass transition temperature behavior. We see a local maximum in the loss modulus and a sharp decrease in the storage modulus. And so you can see we have this sort of glassy behavior at temperatures below TG and sort of more rubbery temperatures at temperatures greater than TG. But we know, kind of from our earlier discussion, that nylon is a semi-crystalline material. So at higher temperatures, we still have a pretty high modulus. This is about a few 200 or so megapascals. And that's up until we get to point number 2. And this is the melting temperature of those crystalline domains. So at about 200 degrees C, we see this sharp drop off in the modulus. I would say it goes, what's probably happened here during this test is the DMA actually kind of gave up. Because once it kind of measures, basically can't measure a modulus anymore, you have something that's much more liquid-like, basically outside the machine's capabilities of measurement. So I saw a couple of questions about the DMA, so let me someone asked if TG in most polymers depend on absorbed moisture. Yeah, that's absolutely true. It depends on a lot of things, but absorbing moisture or even other kind of small molecule components tends to plasticize the material and decreases the TG. Someone else asked, is there any disadvantage of the DMA system having the load cell placed on the driving, moving side? Fundamentally, for 99% of applications, no, there's no disadvantage to that. Very rarely will that be a problem, and it's a little bit beyond the scope of our discussion today, but it's kind of a good thing to point out in terms of the kind of the actual mechanics of the device. But for doing something like this temperature sweep, you would never worry about something like that. It's only when you're doing kind of very, very thin or very compliant materials where you start to have inertial effects that kind of start to wash out your signal. So at higher frequencies as well is where that's a problem. But that tends to be, in my experience, kind of what I'm going to call more exotic materials than kind of standard polymer materials. Let's see, another new question. What about the loading frequency? Will that affect the DMA? Generally, yes. I mean, that's a question of material response. We're going to see a little bit here actually in the next couple slides about how changing the frequency can measure, or measuring the modulus at different frequencies. We can kind of use that to our advantage. That's kind of an intrinsic material behavior question. So polymers tend to have time-dependent kind of viscoelastic behavior, and so changing the frequency changes the modulus of the material. So I want to talk a little bit about time temperature superposition. This is kind of an advanced, primarily DMA measuring technique where we're using the time temperature equivalence hypothesis essentially to our advantage to try and measure or at least forecast the behavior of the material under conditions that we can't actually measure, right? And so you think about it this way. So we have what we're calling the reference temperature, and that's like your operating or use conditions. So for something, a product that you expect to be used at room temperature, your reference temperature should be 23 degrees Celsius or something equivalent. And what we can do is, if we're interested in, let's say, the long-term creep performance of a material using that device, we test it at a higher temperature, because when we test at a higher temperature, we are essentially taking those long time deformation mechanisms of the material, and we are reducing the time scale over which they operate using a higher temperature. And so within our kind of measurement window, let's say we're running a test that lasts an hour, something that would normally take a year at room temperature perhaps only takes an hour at 60 or 70 C, just to put some random numbers there. Now, conversely, if we're interested in the high frequency behavior of our material, so this is for something like a vibration application, NVH, noise, vibration, and harshness, then we use lower test temperatures to kind of take those high frequency deformation modes of the material, kind of freezing them and slowing them down so that we can measure them using the kind of frequency window that our DMA is capable of. So we're going to use high temperature tests to estimate our material behavior at long times or low frequencies. We're going to use lower temperatures to measure material behavior at short times or high frequencies. How does that look more practically, or at least in sort of cartoon fashion? So this is synthetic data. So what's over on the left, these are the storage and loss moduli of material that we kind of have measured at different temperatures. And so then we shift those curves along the frequency axis to create what's called a master curve. And what I want you to look at is kind of the frequency domain on this left-hand figure, the original data, and the frequency domain on the right-hand figure, which is the kind of the master curve, the time temperature superposition master curve. So the test frequency, on our DMA kind of maxes out at about 100 hertz, kind of give or take. And then the lowest, we probably could do it at lower than 0.01 hertz, but those measurements take a really, really long time to do because your kind of test time is inverse of your test frequency. So when we create this master curve, we can start to predict how this material will behave at higher frequencies by using that lower temperature data. So we can look at that a little bit more practically. This is on an elastomer. I believe it's a nitrile rubber, but I don't remember exactly what it is. And so what you can see here are the kind of the original test data. This is kind of generated between 0.01 and 10 hertz on our DMA, and then measured at different temperatures. So the kind of yellow colored ones, those are the higher test temperatures. That's 30 degrees Celsius, measured all the way down to negative 40 degrees Celsius. And so every different color is a kind of a different test at a different temperature. And to do the time temperature superposition process, what we do to shift those along the frequency axis is kind of let the material sort of guide us in this TTS process, and we get the master curve, which looks like this. It's sort of self-similar behavior of the material. And you'll notice that even though we only ever actually measured the material behavior at 10 hertz, we're making predictions up to about 10 to the 9 hertz, something like that. On with this, so the idea here is to quickly generate a linear viscoelastic description of the material behavior over these many orders of magnitude in frequency. The emphasis on kind of quickly generating this material behavior, because the advantage of this is that we don't have to do any sort of otherwise advanced material characterization at extremely elevated frequencies. Now, conversely, we can also do time temperature superposition under creep deformation. So this is when you're concerned about the long time, sort of the storage conditions, long-term deformation of your material under load. So this is just an example from an epoxy. We measured the strain as a function of time at 3 different temperatures under the same applied stress, and then we shift them along the time axis to create this master curve here. And so from tests that I believe these ran about 30 minutes, we're able to make predictions of the creep strain in the material for about 2 years. Now, I get this question, I think, every time we talk about this, every time a new client asks about this, which is to say, how do we know that these predictions are valid? And there are some ways of kind of probing the TTS, it's called the thermal rheological simplicity of your material, while you're doing the testing. But there's not really, in my opinion, a good way to identify whether or not these are valid without actually running a 2-year test. And so that is actually something that we recommend quite often, which is that we start by doing a time temperature superposition characterization. We now have some information that allows us to make these predictions quickly, right? So we can start to compare different designs for our product. We can compare materials and see which one puts us in a riskier spot. And kind of while we're going through that design process, we can also run long-term creep tests to validate both our TTS predictions as well as get more robust data for our actual design process. Let's see, someone asked, how do you do the shift in slide 23? Is it a calibration procedure for materials? Yeah, so the actual shift is kind of that's the right way to phrase this. You basically, if you just compare the 40 and 30C curves, for example, you can tell that we're going to shift the 40C curve to the right to make it so that the two curves overlap. And so kind of the general algorithm is you're reducing the total line length based on some function of the shift factors. It is, I'm going to call it 85% a science and 15% an art. This is not something where, for all materials, I would expect kind of a new practitioner to do a kind of a good job. And it does take some experience. It takes a little bit also knowledge of the actual structure of the material and kind of what you expect of the behavior to kind of make sure that you are kind of keeping your predictions within the realm of or as accurate as possible is what I should say. So it is not something that I think should be done lightly, but it is something that is very powerful when done correctly. So I'd like to move on from the DMA to the DSC, or differential scanning calorimeter. I want to spend a little bit of time to kind of discussing exactly how this technique works, because DSC is extremely powerful, but is, I think, very counterintuitive to understand, or at least unintuitive to understand. So DSC is a calorimetric method, meaning that what we are doing is, if you look at this kind of cartoon image over on the right, so we take small amount of sample. Did I go too far? I did go too far. There we go. We take a small amount of sample, usually around 5 to 10 milligrams, so a very, very small amount. And that's one of the powerful things about DSC, is that we don't need very much material. It doesn't need to be in a nice shape. Whereas for something like a DMA test, it's a mechanical test. We need a sort of flat tensile sample or cantilever bending sample or something like that. For a DSC test, we just need a fragment that is even as small as a half a milligram, if that's all you can generate. What we do is we place that sample in a crucible and then place that crucible in a furnace next to a reference crucible. And so what we're prescribing during the test is a heating rate. So we're going to heat up these, both of these crucibles at a nominal heating rate, let's say 5 degrees Celsius per minute. It's kind of a standard number. What we're actually measuring is the energy required to heat up our sample pan at that specific heating rate relative to the reference pan. And so what's actually reported during the DSC test is the difference in heat flow between these two pans. So what we're going to expect is that as we approach phase transitions for our sample, phase transition temperatures, it's going to change how much heat is required to maintain that constant heating rate. So as you can think of an example I like to give is the latent heat of vaporization of water. So we all know that if you heat water up to 100 degrees Celsius, it'll start to boil. But there's also some extra heat that you need to put in to kind of convert the liquid to a gas, that latent heat of vaporization that's kind of intrinsic to the phase transformation process. Exact same thing in polymers when we undergo things like the melting temperature. It's a little different for the glass transition temperature. We're gonna discuss that right now. So Now, I'll tell you, before we actually look at some data, from a DSC test, we can measure the glass transition temperature, TG, we can measure the melting point and percentage crystallinity of semi-crystalline materials. We can observe what's called cold crystallization. We'll talk about that. We can sometimes measure the material's heat capacity. That's kind of an advanced DSC method. Not all DSCs can do it. And chemical reactions like thermoset curing. So we'll talk about that in more detail in a minute. So as I said, in most DSC tests on polymers, the material is heated at a constant rate. It's usually between 1 and 20 degrees Celsius per minute. And this just some example data that I pulled from the literature on polystyrene is shown at right. So PS polystyrene. So polystyrene is an amorphous polymer, and so we don't expect any melting or crystallization. And so what happens when we heat up the sample of polystyrene is we see this little step in the heat flow curve, right at around 100. It's about 95 degrees Celsius. So that's indicative of the polystyrene's glass transition temperature. So for amorphous polymers, this is as big a feature as you're going to see, or really the only feature you should expect to see on your DSC trace. In contrast, we talked about PET already. It is naturally a semi-crystalline polymer. However, it can be processed, and usually is, to suppress that crystallization, meaning that so that it will stay clear. So as we heat up PET, you'll see that we have a glass transition right at around, I think it's 80 degrees Celsius for this PET. But then we see this kind of upwards peak in the DSC trace. That is the PET crystallizing. So essentially, we've heated above its glass transition temperature. Our polymer chains are more mobile, and they want to form those nicely ordered crystalline domains. And so that's where we see this peak. This is an exothermic process where it's releasing heat. And so that's why we're measuring this peak. Now, as we then increase the temperature, we see this negative peak in the heat trace. This is an endothermic process. This is melting of those crystalline domains that we just formed. And so one thing you might notice is that I think just by looking at it, the area of this melting peak is probably larger than the crystallization peak. And so what that means is that there was actually some crystalline domains in our PET already. So we just crystallized some more, but then we melted them all. And so, functionally, what this might mean to you if you're thermoforming PET is that you need the material to be soft. So you need to heat it above its glass transition temperature, but you don't want it to crystallize. So you need to make sure that your temperature stays below this kind of threshold. Is maybe 110 or so degrees Celsius. And so if you would like to thermoform this PET, you need to make sure that your temperature stays between those two temperatures. Now, using DSC to measure chemical reactions is a different thing that can be done, especially for something like a thermoset epoxy. This is from a case study that we worked on where kind of comparing essentially two different adhesives, one that we're calling serviceable and one that kind of failed during service. And so if we look at the DSC traces, we can see that the serviceable adhesive has a higher glass transition temperature than the failed adhesive. And then we see this large exothermic peak in the failed adhesive, whereas the serviceable adhesive really has a much smaller peak. So if you measure the area under these peaks, we have about 20 joules per gram versus 3.5 joules per gram. And so the energy here, corresponds to the chemical reaction between the epoxy and the amine groups in this epoxy adhesive. So our interpretation of this is that this failed adhesive was not fully cured during the production process. And we can tell because there's a lot of unreacted monomers, functional groups that are cross-linking as we heat this up above the glass transition temperature, and not nearly as much in the serviceable adhesive. The next technique I'm going to talk about just very briefly is called TGA, or thermogravimetric analysis. This is a bit more intuitive than DSC. So in this type of test, we take a similar small amount of material and we heat it up in an inert atmosphere. And all we're measuring is the mass loss of the sample versus temperature. And so TGA is largely used to do things like measure solvent absorption. So if you have kind of moisture in your sample and you want to figure out how much there is, maybe compare different storage conditions or something like that. TGA would be very useful for that. You see kind of the onset of thermal degradation. So as we heat these PTFEs up, you can see that they start to degrade at about 500 degrees Celsius. So that's a good way a very quick way to kind of identify an absolute maximum use temperature for that material. And then the other thing that TGA is really good for is kind of measuring the inorganic content in the material. So kind of a standard TGA test is you actually heat the material up to 600 degrees C in nitrogen and then switch to either air or pure oxygen and heat it up the rest of the way. What you're really trying to do is essentially burn out all of the organic content and just measure essentially how much, let's say it's a glass filler, is in there. So if you're trying to reverse engineer something or trying to figure out exactly how much inorganic is there, TGA is a really quick way to kind of set that baseline for you. Some questions here. What about TTS? We'll go back to that at the end. So slide 27 is TG always before a crystallization peak. If the material has already crystallized, then no. So you will only see that crystallization peak in something like a clear PET where the crystallization has been suppressed. And someone else asked if TG is a range or a discrete value, depending on if it's a thermoplastic versus thermoset. So the thermoplastic versus thermoset wouldn't change how I would report the TG for the material. I'd base it on either a DMA test or a DSC test. And that's the right way to answer this. I like to think about it as a range, but when you're comparing materials, it is sometimes just helpful to have a single number. So it's usually the way I like to do it is kind of report the TG so that we can compare to, let's say, a specification sheet or a different material. But when we're thinking about setting, let's say, a maximum operating temperature for our material, to think about it as a range. And so it's just helpful to kind of keep that in your head. So next technique I want to talk about is FTIR, or Fourier transform infrared spectroscopy. This is a chemical spectroscopy technique that is sensitive to molecular functional groups. So this image is something I've just taken from Agilent's marketing material. They're looking at it's basically a 3-layer film. And you can see the IR spectra over on the right of each of the 3 layers of the film. And you see that this is absorbance as a function of wave number, which is how FTIR spectra are typically reported. And each one of these peaks in the spectrum corresponds to essentially a different functional group within the polymer. So this very strong peak right around 1750 in the PET, that corresponds to this carbon double bonded to an oxygen. This peak over here at around 3300, this is an amine group. And then this is about 2915 inverse centimeters. This is a carbon bonded to a hydrogen. And so you can see that we have all these different peaks, and they all correspond to kind of slightly different functional groups of the material. This is kind of like the material fingerprint, essentially, right? So if we were able to figure out and assign each one of these peaks to a different functional group, we would have a decent sense about what functional groups are in the molecule in question. And one thing I like pointing out here is that this middle layer they've identified as nylon. It also has a carbon double bonded to an oxygen, but it's at a slightly different wave number than the carbon double bonded to an oxygen here in the PET. And so that's because it's not just the functional group, it's actually kind of the surrounding environment that also helps determine the actual specific wave number where the absorbance band appears. So, what I find FTIR to be kind of useful for in 95% of the applications is purely a material identification. So if you have some question about the provenance of your polymer, you don't know what the base material is, you're worried your supplier gave you the wrong material, you take an FTIR spectrum. This is non-destructive. It takes only a few minutes really to collect the data, compare it to a database. That database can either be something that you have generated. You have your historical library of FTIR spectra, and so you can say, this one is different. Now you have kind of ammunition to go back to your supplier and say, why did you send us the wrong material? Or you can compare it to, there's kind of a databases that you can buy that will have tens of thousands of entries in them. That's especially helpful if you have a general question about what that material is, and for some reason are unable to get that information from somewhere else. But you can also kind of do other more kind of advanced characterization or advanced techniques with FTIR. So for something like an adhesive curing process, you can see in this epoxy that the kind of peak heights of these different functional groups are changing as we go through the chemical curing reaction. So you can use that to calibrate a cure model. Kind of skipping through these because I see we're getting towards the top of the hour. Another example is kind of the spatially varying chemical composition of your material. So use what's called an FTIR microscope. So you have about 10 micron spatial resolution in your FTIR spectra. And so you can sort of take spectrum, on this sort of like 10 micron scale steps to see how the composition, in this case, this is a solvent weld between a PVC pipe and an ABS fitting. So you kind of measure what, called the width of this diffusion zone to help you understand more about perhaps the kind of the performance of that interface, maybe compare different materials. And so now we reached the end of the techniques that we wanted to talk about. And so just to kind of reflect on what we've discussed today, primarily, we talked, especially at the start, about the kind of chemistry and structure of polymers, plastics, and adhesives. And I hope you have some more understanding of the different categories there are and how they're correlated with some of the functional, especially mechanical properties of materials, as well as technical processing conditions. We talked about semicrystalline and amorphous polymers, thermosets and thermoplastics, and then understanding whether the material you're working with is crystalline, semicrystalline, or amorphous, it's thermoset or thermoplastic, really influences how you should think about using that material, applying that material, how you expect it to behave under loading conditions or elevated temperature, things like that. And then, in the second half, we talked about these analytical techniques. And I know we went through this very quickly. There's a lot of information here. So I'm hoping that, you got enough information so you know what questions you want to ask. There's much more that you can learn about any of these techniques and how they can be applied, especially when kind of driving a product to market and driving it through that R&D phase that most of our clients tend to work with. So before we conclude here, I do want to just put in a few plugs. So one is we have our ongoing free webinar series, which many of you know about already since you are here. But upcoming over the next couple of months, we have a webinar on combination products of medical devices. There'll be a little bit more kind of applied engineering that we do here at Verist. Another webinar in March on interfacial stress and delamination in layered structures. So that's will be a bit more of kind of an academic applied science talk, if you will. And same with the next one at the end of March in mixing and chemical reactions. So some of our fluid dynamics experts, I can't remember who's in charge of that one. We'll be talking about mixing and computational modeling and basically how to use that to kind of drive process improvements. So if you go on our website, you see I put the link at the top here, but if you go to our free webinars page, you can sign up for our email list and you'll get notifications when we post these. And then the last thing that I want to mention is that we are currently hiring here at Verist. We have basically two positions that we're actively hiring for right now. The first one is the Polymer Materials Engineering Consultant. So if you stuck through this whole webinar and you feel like you didn't learn anything, then I think you're highly qualified for this job. So please do go to our website and fill out that application. The other one is for a multi-physics simulation consultant. So if you watch this webinar and said, I learned a lot, and I have lots of experience with multi-physics simulation, then I would encourage you to go to our website, fill out that application as well. Okay, I know there's at least one question that I skipped and wanted to go back for. Let's see. It's about how to actually draw the TTS master curve. So I'll go back to, this is slide. There we go. So the kind of the scientific approach is there's a couple different ways of answering this question. I guess I should restate this for everyone. Basically, can you elaborate more on how to draw the TTS curve for 2 years from testing the epoxy in 3 different temperatures? So you have to remember that the kind of fundamental assumption that we're making, and it is an assumption, it is not something that is easy to justify without actually fully doing the 2 years of testing, right? Is that this material is fancy word is thermorheologically simple, meaning that we can use this sort of like time temperature equivalence is a good mental model for the material's deformation behavior. The kind of more physical description of that is that the creep deformation of the material is controlled by kind of a set of mechanisms that have uniform temperature dependence. So for almost all polymers, they will deform because the polymer chains are essentially sliding across one another, right? And so if for a particular material, we increase the temperature, they're able to slide faster, essentially. So the deformation will be faster. And you can see that even just in this data. As we go from 30 to 40 to 50 C, as we apply that step strain and measure, step stress and measure the strain, we measure a lot more strain at 50 C for a given time, let's say at 10 seconds, than we do at 40 or 30 C, right? And so what we're doing when we do this sort of master curve time temperature superposition process is estimating basically the temperature dependence of that deformation mode, which is to say that if we so then the other way to kind of answer your question is that we are just looking for similarity between these curves, right? Because the assumption that we're making is that in this case, if I measure the creep deformation at 40 degrees Celsius for 10 to the 4 seconds, at 40 degrees Celsius, it is equivalent, so it's probably going to be about, excuse me, 10 to the 4 seconds at 25 degrees Celsius is going to be about equivalent to measuring the deformation at 40 degrees Celsius for, it's going to be about 10 seconds or something like that. And so we're making the assumption that the self-similarity between these curves is descriptive of the physics of deformation of the material. And so the more mathematical description of how this curve shifting works is that we're only shifting along the time axis. There's no vertical shifting here. You can occasionally use vertical shifting in other contexts. I prefer not to if I don't have to. It's less physically justified in my opinion. In some cases it is kind of opening a can of worms there. But basically you hypothesize a shift factor and then you're minimizing the total line length essentially, normalize, I can't remember exactly how that's done, as a function of that shift factor. Because you can imagine that if we sorted all these data points by their time and then drew a line between them, we would jump from here up to here, down to here, up to here, down to here, down to here, and the length of that line would be very long. As we shift these on top of each other, and as we get a nice superposition master curve, the length of that line is much shorter. And so that's kind of effectively how these algorithms work. In practice, when you have a DMA, it will be built into their software, and there's not a lot of work you need to do kind of manually for that. Where the work comes in is when you have a kind of a non-standard material or superposition that is limited in certain ways, essentially at higher temperatures or higher stresses and things like that, where you need to use your engineering judgment using your knowledge of the material structure to kind of justify whether or not we're going to accept, quote unquote, the predictions of the TTS master curve. Right. We are right at 2 o'clock, I think. I'm just going to check all the questions in here that I can see. I think we've talked about all of those. If not, you can see my email at the bottom of the slides. Please feel free to send me an email. Last question I got is, can you share the slides and recording? So you should, sometime today or tomorrow, you should receive a recording of this presentation. That should go out automatically, and I'll make sure that it does. Other than that, if there are no more questions, we're right at 2 o'clock, so I guess I ran over a little bit, but we did answer some questions along the way. So thank you everyone for joining. I hope we'll see you again in our webinar series, and take care.